All right, let's dive right in. We're going to get into the absolute silicon heart of the AI revolution. And trust me, it's a battle of titans, a straight-up technological clash that's going to define, well, everything. We're talking about the AI chip wars. And in the ring, the two heavyweights, Nvidia and Google. Let's get into it.
You know, every time you hear about some new, incredible AI model like Gemini or the next Claude, there's this invisible army of super specialized chips doing all the heavy lifting in the background. They're the engines. So it really begs the question, right? Who actually builds the best engine for AI?
So in one corner, we have the reigning undisputed champion, Nvidia's GPU, the graphics processing unit. I mean, this is the hardware that literally powered the entire deep learning explosion. And in the other corner, we've got the specialized challenger, born and bred inside Google's own labs, the TPU, or Tensor Processing Unit. This is the epic showdown we're going to break down today. Okay, first up, let's talk about the champ. Nvidia's GPUs. They weren't even designed for AI originally, but it turns out their whole architecture was just perfect for it. You got to think of them as the versatile jack-of-all-trades master of computation. So, how does a modern AI GPU actually tick? Well, imagine an engine with like over 100 tiny independent pistons, all firing at the exact same time. These are called streaming multiprocessors, or SMs. Each one is its own little powerhouse, able to handle tasks all on its own. It's this distributed, parallel design that gives the GPU its incredible flexibility. And that right there explains the GPU's biggest strengths. Because it's so modular, it can juggle hundreds of different tasks simultaneously. For developers, this is huge. It often means the GPU just works when you throw some new or even kind of weird problem at it. And it's that adaptability that really cemented its place as the king of the AI world. But, you know, while Nvidia was busy adapting its versatile master, Google was in the lab forging a purpose-built weapon. The TPU was designed from the ground up for one single thing, to just crush the massive matrix math that's at the heart of all neural networks. Now check out the contrast here, because this is fascinating. Instead of hundreds of little cores, a TPU has just one or two massive, incredibly powerful cores. So if the GPU is like a fighter with hundreds of quick jabs, the TPU is a brawler with a couple of devastating knockout punches. Each core is just a specialized beast, built to do one thing, matrix math, and do it exceptionally well. And this super specialized approach, it's got some serious perks. Because the design is simpler, more focused, TPUs are generally cheaper to build. And since they are so purpose-built, it's often way easier to squeeze every last drop of performance out of them. They are the absolute core of what Google calls its AI hypercomputer, a whole system designed for insane, efficient scale.
So we've got the flexible GPU versus the focused TPU. But what happens when we put their latest and greatest models head-to-head? Let's get to the tail of the tape. Nvidia's Blackwell B200 versus Google's brand new Ironwood TPU.
Okay, let's talk raw, face-melting power. First up, Google's Ironwood TPU. It clocks in at a staggering 4.6 petaflops. Now, what does that even mean? It's 4.6 quadrillion calculations every single second. For a long time, this was Nvidia's turf, no question about it. But yeah, those days are clearly over.
And Nvidia's B200, it comes in right at 4.5 petaflops. This is a huge deal. For the first time ever, the raw compute power is pretty much identical. The performance gap, it's officially closed.
But hey, power isn't everything. These chips need a massive amount of memory to hold today's gigantic AI models. Google's Ironwood, it comes packed with 192 gigabytes.
And Nvidia's B200? Yep, you guessed it, a perfect match. Also with 192 gigabytes. On the core specs of power and memory, these two titans are now in a virtual deadlock.
So let's look at the full comparison. Performance, memory capacity, nearly identical. Now, Nvidia does still hold a slight edge in memory bandwidth and a pretty significant lead in that direct chip-to-chip interconnect speed. But look, on paper, Google's Ironwood has proven it can absolutely compete at the highest level. This isn't a David versus Goliath story anymore, not by a long shot. But this is where the story gets really interesting. See, training a massive AI model isn't about one chip. It's about networking tens of thousands of them together into one giant supercomputer. And this is where the two companies have fundamentally different philosophies. It's not about the strength of a single soldier, it's about the strategy of the entire army. Nvidia uses a more traditional, hierarchical approach. You have small groups of GPUs, called nodes, that are all tightly connected to each other. Then, these nodes get linked together using these incredibly powerful, but also very expensive and power-hungry central switches. You can think of it like a corporate org chart where information has to flow up and down through central managers.
And then you have Google. Their approach, it's completely different. They use this wild thing called a 3D torus. So forget about those central switches. Just get them out of here. Instead, every single TPU is wired directly to its neighbors, up, down, left, right, forward, back, in this giant three-dimensional grid. It's totally decentralized, a pure peer-to-peer network. It's way more like a social network than that stuffy corporate org chart.
And this slide just sums up the trade-offs perfectly. With NVIDIA's switches, any two chips can talk with very few hops, which is awesome, but those switches can also become bottlenecks. Google's Taurus design gets rid of the switches entirely, which saves a ton of cost and power, but it also means a message between two chips on opposite ends of the grid might have to take a lot more hops. And just look at the difference in scale. NVIDIA's biggest single unit is a rack of 72 GPUs. Google builds pods of over 9,000 TPUs. It's just a different world.
Okay, so we've got these two dueling philosophies, right? A flexible chip in a switch network versus a specialized chip in a massive mesh network. So how does this actually play out in the real world when you're trying to train the next world-changing AI model?
Well, some of the biggest players in the game are placing their bets. Anthropic, the company behind the Claude models, and a direct competitor to Google's own Gemini, by the way, is going all in on TPUs. When you hear a company plans to use up to 1 million of them, well, that tells you everything you need to know about their confidence in Google's massive scale strategy. Now, this is really interesting because it shows a huge practical difference in efficiency. To get a GPU running at its absolute peak, you have to feed it a really large batch of data all at once. We're talking around 2,500 tokens or pieces of text for every single chip. But because of its simpler, more focused design, a TPU can hit its peak performance with a much smaller batch size, around 850 tokens. And that difference can have huge implications for training efficiency and ultimately cost. But, even with all these incredible hardware advancements, this fight is far from over. Because as the physical power of these chips starts to look more and more similar, the real differentiator, the next great battlefield in these AI wars, is going to be software. The compilers, the frameworks, the tools that let developers actually unlock the full potential of these silicon armies. And that leaves us with the ultimate question. In this relentless, nonstop race to build artificial intelligence, what's the winning strategy? Is it the unbelievable flexibility of NVIDIA's versatile master, a chip that can adapt to any challenge thrown its way? Or is it the focused raw power of Google's specialized weapon built for one purpose and one purpose only, to scale to infinity? The answer is going to shape our future.